Welcome to the Deep Dive, where we plunge into a stack of complex information and distill it into something genuinely understandable and, dare I say, captivating. Today, we're taking a deep dive into the incredible world of large language models, or LLMs, you've seen them everywhere, right? Powering creative writing tools, sophisticated chatbots, generating text that reads like a human wrote it, answering your most obscure questions, and even performing truly complex multi-step reasoning. It's nothing short of remarkable, really.
Indeed, it's quite stunning. These models have utterly transformed the landscape of natural language processing and well beyond. Their ability to approximate human-like cognition in real-world settings is quite profound. And it all stems from leveraging these vast amounts of self-supervised training data.
But as amazing as these models are, and they really are amazing, they're not perfect, not by a long shot. If you've used them, you might have noticed them hallucinating, which is a rather polite term, isn't it?
Oh, yes. Polite for generating factually incorrect or sometimes quite misleading information.
Exactly. And they can struggle with logical consistency, especially over longer pieces of text. And sometimes, frankly, they just don't quite behave in the way we want them to or align with what we as users actually expect. And this isn't necessarily a problem with their raw intelligence, right? It's more about refinement.
That's a great way to put it, refinement. What's fascinating here, and this is really key, is how the research community has shifted its focus. It's no longer just about building the biggest model possible, throwing more data at it.
Right, not just brute force.
Exactly.
Yeah.
The focus now is increasingly on these intricate post-training methods, and this highlights a crucial distinction. While LLMs can produce responses that look logically coherent, and they can even do some sophisticated multi-step reasoning.
Yeah, sometimes it feels like they're really thinking it through.
It feels that way, but their reasoning is fundamentally distinct from human-like logical inference. It's different. They operate in this implicit probabilistic way. It's all based purely on statistical patterns learned from data.
Okay, so not actual logic rules, more like statistical guesses based on trillions of examples.
In essence, yes.
Oh,
Extremely sophisticated pattern matching and prediction. And this really raises an important question for all of us. How do we ensure these incredibly powerful models align precisely with human intent? How do we make sure they provide outputs that are truly useful, that are what you actually want and need, especially in real-world, sometimes tricky scenarios?
exactly. And that's our mission for today. We're going to take a deep dive into these crucial methodologies, unpacking how LLMs are refined beyond that initial massive training phase. Think of it like this. I mean, like a high-performance race car. Pre-training is like building the engine, the chassis, the core mechanics that's laying the broad linguistic foundation by feeding it the whole internet, basically.
Right, building the raw power.
Yeah. But post-training, that's the fine-tuning, the calibration, the adaptive systems. That's what makes it not just fast, but precise, reliable, and safe on the track, even when conditions change. It's about teaching it how to drive skillfully, not just how to start the engine.
An excellent analogy. And to navigate this complex terrain, we'll explore the three main categories of these post-training techniques. First, we'll look at fine-tuning, which is all about tailoring the model for specific tasks.
By making it a specialist.
Precisely. Second, reinforcement learning, which is really about teaching the model what we humans prefer, aligning it with our values and expectations.
The how to behave part.
Exactly. And finally, test time scaling. This boosts performance right when the model is generating an output for you, making it smarter on the fly. Each of these plays a really vital role in transforming a powerful but maybe unpolished model into a truly sophisticated, user-aligned AI that you can actually rely on.
Okay, let's unpack this then. We're talking about what happens after these massive brains are built. How they learn to really think, or at least act like they think and behave in ways that are genuinely useful, accurate, and safe for you, the user. So let's start with the absolute basics, just to make sure we're all on the same page about the foundation here. LLMs begin their lives, if you will, by essentially predicting the next word, or token, technically.
Token, yes. A word or part of a word.
Right. They do this using absolutely vast web-scale amounts of data, and the technique is called maximum likelihood estimation, or MLE.
Correct. MLE. It's about maximizing the probability of the observed data.
So this process gives them an incredibly broad linguistic foundation. They grasp grammar, vocabulary, the general flow of human language. It's quite impressive.
It really is. And what's even more remarkable, perhaps, is that when they're trained on diverse data, including things like computer code, mathematical equations, scientific papers.
Not just websites and books.
Exactly. When they see that diversity, they even start to show what researchers call emergent reasoning abilities. They seem to pick up on patterns that look a lot like logical deduction.
Wow, okay, so they learn how to sound logical just from the data.
It appears so. Pre-training provides the statistical likelihood of sequences. It learns what words or phrases are most probable to follow others based on the massive data sets it's consumed. And this is incredibly powerful for generating fluent, coherent text that sounds natural, almost human.
Yeah, sometimes spookily human.
But, and this is a big but, despite this broad foundation and these emerging capabilities, there's a significant gap. Pure pre-training, just the MLE part, often leads to models that are prone to factual errors, those hallucinations we mentioned.
This polite term again?
Yes. And they can struggle to maintain logical consistency over long conversations or complex arguments. Multi-turn sequences are hard, and critically, they don't inherently align with nuanced user expectations or, frankly, desired ethical or behavioral standards.
So it might say something technically possible based on the data, but totally inappropriate or unhelpful in context.
Precisely. In ambiguous situations or even malicious ones, if prompted incorrectly, a purely pre-trained model might generate something harmful or nonsensical simply because similar patterns exist to its training data. Not because it's the best answer or the safest or what you actually wanted, it's just statistically probable based on its past diet of text.
So it's not enough to just give them all the books in the world, right? You can't just dump data on them and expect a perfect assistant. They need a bit of guidance, schooling, on how to actually use that knowledge responsibly.
Guidance is a good word. Schooling, maybe. That's precisely where post-training comes in. It's not just one thing. It encompasses multiple rounds of fine-tuning and specialized alignment mechanisms. The overarching goal is to refine the model's behavior, mitigate those inherent limitations, like biases baked into the training data, or the tendency towards inaccuracy, and truly align the LLM's outputs with human intent and practical utility.
Getting it to do what we want it to do.
Yes. It's about moving beyond what's statistically probable in the training data to what's truly useful, accurate, and safe for you, the individual user interacting with the model right now. And this comprehensive approach, which we'll delve into, includes these advanced techniques like reinforcement learning and various scaling methods, all designed to ensure robustness and adaptability in real-world applications.
This distinction between pre-training and post-training, it also helps us understand something really fundamental about how LLMs reason. Because it's not quite like us, is it?
No, and this is such a crucial nuance. It gets to the heart of what LLMs truly are, or perhaps what they aren't yet. While they can produce responses that appear logically coherent, and they can even perform these sophisticated-looking multi-step reasoning chains.
Which is what makes them seem so smart.
Exactly. But their reasoning is fundamentally distinct from human-like logical inference or symbolic manipulation. Humans perform explicit logical deduction. We manipulate rules and facts directly, consciously. LLMs don't seem to do that.
So how do they do it then?
They operate in an implicit and probabilistic manner. They recognize and generate logically coherent responses purely based on statistical patterns they've learned from the data. It's not because they understand the underlying logic in a human sense, or because they're applying formal rules like we might in math or logic.
Okay, here's where it gets really interesting for me. It's like they're incredibly good at connecting the dots. They know that the dots connect in certain ways based on the data, but they don't necessarily understand why the dots connect. Is that fair?
That's a very good way to put it.
Yeah.
This probabilistic nature explains why an LLM might produce a compelling, seemingly reasoned output, but still stumble on what seems like a relatively simple logical task that a human would solve easily. They are phenomenal pattern matchers and sequence predictors. They're not explicit logicians in our human sense, not yet anyway.
Okay.
And if we connect this to the bigger picture for you, the listener, it means that while raw scale from pre-training gives them these impressive capabilities, these specialized post-training strategies aren't just about improving performance metrics on some benchmark. They are absolutely essential. They bridge the gap between what's statistically probable based on web text and what's truly reliable, useful, and aligned for you, especially in scenarios demanding precise logical consistency or strict adherence to your specific instructions.
So it's about making them trustworthy.
Trustworthy, useful, aligned. It really raises that important question. Can this kind of statistical inference truly replicate human-like critical thinking? Or is it an incredibly powerful approximation that still requires this human-guided refinement post-training? The current state of the art, all the work we're discussing today, strongly suggests the latter. Post-training is where the magic happens for real-world use.
Okay, so with that foundational understanding, the difference between raw pre-training and necessary refinement, let's move into the first major pillar of post-training. Fine-tuning. This is really about tailoring LLMs for specific tasks, right? Making them much more useful in diverse applications, almost like giving them a specialized skill set after their general education.
Exactly. Think of it as moving from a generalist to a specialist.
Right. So first up, we have instruction following and conversation fine-tuning. You know how you can go to an LLM, type in a really specific command like summarize this article in 3 bullet points, but only use positive language, and it just gets it most of the time.
Yes, hopefully. That capability comes largely from instruction fine-tuning.
Okay, explain that.
So this technique specifically adapts the pre-trained LLM to follow user instructions accurately and helpfully, regardless of the specific task domain. It involves further training, but this time on meticulously curated diverse data sets. These data sets consist of pairs, an instruction or prompt, and a desired response or completion.
So you show it lots of examples of following orders correctly.
Pretty much. Thousands, maybe millions of examples. This is what allows models to truly understand and adhere to your directives, making them far more versatile than the base pre-trained model. We've seen models like T0, FLN, Alpaca, Vicuna. They demonstrate significantly enhanced instruction following. They often outperform their base versions on zero-shot or few-shot tasks they haven't explicitly been trained on, simply because they grasp the intent behind the instruction much better.
Okay, that makes sense. And then there's dialogue, multi-turn, fine-tuning. This is how they learn to be good listeners, right?
Yeah.
Not just spitting out one answer, but having a back and forth.
Exactly. This is how they learn not just to talk at us, but with us. If you've ever had a longer conversation with an AI chatbot, and it actually remembers what you said 5 messages ago.
Which is still kind of amazing when it happens.
It is. That's dialogue fine-tuning at work. It's explicitly focused on handling these multi-turn conversations. The key is ensuring the model maintains context across turns, remembering the thread of the conversation, and produces coherent and relevant replies in a chat format. This makes the interaction feel much more natural and dynamic for you.
So models like ChatGPT or LaMDA, they've had a lot of this.
Oh, absolutely. They feel much more interactive and context-aware, precisely because of this specialized dialogue fine-tuning. Now, there's some overlap with instruction fine-tuning, of course, because many instructions might come within a chat format. But using dedicated multi-turn conversation data leads to a much more natural, engaging user experience. They effectively learn the rules of conversational interaction, just like we do.
Okay, so fine-tuning helps them follow instructions and chat properly. But can it also make them like deeper thinkers or experts in specific areas?
Yes, absolutely. Beyond just following instructions, fine-tuning plays a critical role in deepening an LLM's understanding and enabling true specialization. One really interesting area here is chain of thought, reasoning fine-tuning.
Chain of thought, we hear that term a lot.
You do, and it's important. This technique teaches models to produce step-by-step reasoning traces instead of just jumping to the final answer. Imagine you're working on a complex math problem. You wouldn't just write down the answer right. You'd show your work.
Hopefully, yeah.
Co-fine-tuning helps LLMs do the equivalent. By explicitly showing the intermediate rationales, the thoughts, it significantly improves interpretability. It lets us see how the model arrived at its conclusion. And crucially, it often enhances accuracy on complex tasks, things like multi-step math word problems or multi-hop question answering, where you need to connect multiple pieces of information.
How do they teach it to do that? More examples.
Essentially, yes. It often uses supervised reasoning annotations. These might be handcrafted by human experts, showing the ideal step-by-step solution. Interestingly, sometimes even simple phrases you include in your prompt to the model, like "let's think step by step," can trigger this kind of coherent step-by-step reasoning in sufficiently large models that have seen codey examples during fine-tuning.
Huh. So you can prompt it to show its work.
You can. And this has even been extended to multimodal models, models that handle images and text. Fine-tuning can integrate image analysis, question answering, and codey reasoning steps all together.
Okay, and what about that specialization you mentioned, making it an expert?
Right, that's domain-specific, specialized fine-tuning. This is what you do when you need an LLM to be a true expert in a very particular field, maybe biomedicine, finance, law, coding. Imagine you're a lawyer. You need an AI that truly understands complex legal jargon, case precedents, specific statutes, not just general
You
English.
need a specialist, not a general practitioner.
It's exactly. Domain-specific fine-tuning involves curating massive corpora of text and labeled examples that are highly relevant to that specific field. You then further train the LLM on that specialized data. We see models like BioGPT, fine-tuned on biomedical literature, Finbert for financial texts, specialized models for climate science like ClimateGPT, or CodeT5 for understanding and generating code. This adtection ensures the model's parameters, its internal connections, really adapt to the unique language, the core concepts, the specific nuances of that field.
And this works for images too.
Yes, it's also been extended to vision language models. You can fine-tune them for interpreting specific types of images like remote sensing satellite imagery, medical scans like X-rays or MRIs, analyzing spatiotemporal video inputs, or even understanding data presented in complex charts and graphs.
Wow. But doesn't that create a potential problem? If you make it super specialized in, say, medicine, does it forget how to talk about the weather? Or does it struggle with things outside its narrow expertise?
That's a very important question, and it points to a common trade-off. As models specialize and become incredibly good at one thing, they can sometimes struggle with outer-domain generalization. Their performance on tasks outside their specialty might decrease. So it's often a balance you need to strike, designing the fine-tuning process to achieve deep expertise in one area while trying to maintain broad versatility. It's an active area of research.
Okay, so fine-tuning sounds incredibly powerful for making these models useful, but it also sounds like it could get very expensive very quickly, especially with these monster models with billions, even trillions of parameters now. If you're a smaller company or maybe a university researcher without access to a giant supercomputer, how do you even begin to afford this kind of specialization? Is there a way to make it leaner, more accessible?
You've hit on a really significant challenge in the field, and the answer, thankfully, is yes. Fully fine-tuning these enormous LLMs is indeed computationally and memory-intensive. It's a major bottleneck. This is exactly where parameter-efficient fine-tuning, or PEFT, comes in. It's a crucial set of solutions.
PEFT. Okay, parameter efficient. Sounds promising. How does it work?
So PEFT methods are incredibly clever. Instead of adjusting all the billions or hundreds of billions of parameters in a huge LLM during fine-tuning.
Which would require massive amounts of computing power and memory.
Exactly. Instead, PEFT introduces only a small set of new trainable parameters, or sometimes learnable prompts, while freezing the vast majority of the model's original weights. The bulk of the model stays locked.
Ah, so you're only tweaking a small part.
A very small part, relatively speaking. Key techniques you might hear about include LoRa, which stands for low-rank adaptation, prefix tuning, and adapters. Think of it like this. Instead of completely rebuilding a massive, complex machine from scratch for a new task, you're just adding a few highly specialized attachments or finely tuning a few specific dials.
Okay, I like that analogy, adding attachments.
These lightweight modules are strategically injected into specific layers or parts of the model. And because you're only training these few new parameters, it dramatically reduces both the memory footprint, how much RAM you need, and the computational overhead, how much processing power is required for the fine-tuning process.
So what does this all mean for us? For you, the listener, or maybe for developers out there?
It means we can get highly specialized, fine-tuned LLMs without needing, a dedicated data center or a supercomputer in the garage. It means you can potentially train a powerful, specialized LLM using significantly less powerful hardware, maybe even on high-end consumer GPUs in some cases, depending on the model size and PET method.
That's huge for accessibility.
It is. And moreover, these PET approaches can often be combined with other optimization methods to squeeze out even more efficiency. Techniques like quantization and pruning.
Quantization and pruning, what do they do?
Quantization, basically, reduces the precision of the model's weights. Think of it as using fewer decimal places to represent the numbers inside the model. This makes the model smaller and faster, taking up less memory. Pruning, meanwhile, identifies and removes unnecessary connections within the neural network, sort of like trimming dead branches off a tree.
Making it leaner.
Exactly. And techniques like kill-LoRa, for example, cleverly combine 4-bit quantization with low-rank adaptation. Thawakar. Tools like Bits and Bytes provide 8-bit optimizers. All these things together make LLM training and fine-tuning much more practical, even on smaller GPUs or more constrained hardware setups.
So combining these efficient tuning designs like LoRa and kill-LoRa with other optimizations really opens things up.
It absolutely does. It enables cost-effective LLM adaptation for all sorts of specialized tasks, like domain-specific text generation, or building a chatbot for a niche topic without the prohibitive expense of full fine-tuning. This is especially valuable for specialized domains, maybe medical research or software development, where getting large amounts of high-quality labeled data might be difficult or expensive. The reduction in trainable parameters makes it far more feasible to use smaller, in-domain datasets and still achieve impressive results. It really helps democratize powerful AI.
All right, so we've covered fine-tuning, which tailors an LLM for specific tasks, making it a specialist, like teaching it what information is relevant for medicine or law. But what if we want to instill something even more fundamental, to teach it not just what to say in a specific context, but how to behave more generally, in a way that truly aligns with our human values, our preferences for things like helpfulness, honesty, harmlessness?
Exactly. This goes beyond just factual accuracy or domain knowledge. This is about shaping the model's interaction style and ethical boundaries.
Yeah, this feels less about facts and more about judgment, values. And this is where reinforcement learning, or RL, becomes crucial.
Right. That's precisely it. RL is the key technique used to align LLMs with these more nuanced human preferences and desired behaviors.
Okay, so how does the core RL loop for LLMs typically work? It sounds complex.
It has a few key steps, but the core idea is quite elegant. It usually follows a three-step process. First, there's often an initial stage of supervised fine-tuning, SFT.
We just talked about fine-tuning, so it starts there.
Often, yes. You start with your pre-trained language model, and then you refine it on a high-quality, human-crafted data set of desirable interactions. Think of it as giving the model a solid baseline for format and style. Teaching it, this is the kind of response we generally like from the get-go. It sets the stage for the more complex RL part.
Like teaching a child basic manners before sending them out into the world.
That's a good analogy, establishing a good starting point. Next, we move to step 2, reward model, RM, training. This is where the human feedback comes in directly and plays a critical role.
Okay, the reward model. This sounds important.
It is. You take the model that came out of the SFT phase, and you use it to generate multiple possible responses to various prompts. Then, human annotators look at these responses and provide preference labels. They might be asked, for example, which of these two responses is better? Or they might rank several responses from best to worst, based on criteria like helpfulness, truthfulness, harmlessness.
So humans are literally grading the AI's answers.
Exactly. Thumbs up, thumbs down, or ranking them. This human feedback data, the prompts, the responses, and the human preference labels, is then used to train a separate model, the reward model. The reward model's job is essentially to learn how to replicate those human preference judgments. It learns to predict, for any given query and response pair, a single score that reflects how much a human would likely prefer that output.
Ah, so it learns to predict human taste, basically.
In a way, yes. It learns a function that approximates human preferences. And sophisticated statistical models, like the Bradley-Terry model, are often used behind the scenes to robustly turn those pairwise human comparisons into a reliable scoring system for the AI.
Okay, SFT first, then train a reward model based on human feedback. What's the final step?
The final step is the RL fine-tuning itself. This is the main event where the actual learning happens for the LLM. The core LLM, which we now often call the policy model in RL terms, is optimized using a policy gradient algorithm. The most commonly used one you'll hear about is proximal policy optimization, or PPO.
PPO, right.
The objective here is simple. Update the LLM, the policy, so that it generates responses that get the highest possible score from that reward model we just trained.
Come on.
You iterate this loop, the LLM generates responses, the reward model scores them based on predicted human preference, and then the RL algorithm updates the LLM's parameters to make it more likely to generate high-scoring responses in the future.
So it's constantly trying to get better at pleasing the reward model, which is trying to mimic human preference.
Precisely. Through this iterative process, the LLM learns to produce responses that humans find preferable across those key dimensions: accuracy, helpfulness, harmlessness, stylistic coherence, whatever was encoded in the human feedback. This is where it goes from just knowing facts to knowing what to do with those facts and how to behave in a way that we, the users, appreciate.
That's a really clever loop, but getting that reward model right seems absolutely critical. How do they design those rewards? It feels like there could be different ways to measure goodness.
You're absolutely right. The art of reward modeling is crucial for effective RL, especially for assigning credit correctly across long, multi-step reasoning processes. It's not trivial. We can broadly categorize rewards. First, there's explicit reward modeling.
Explicit, meaning defined upfront.
Exactly. These rewards are directly defined by specific rules, heuristics, or direct human annotations and ratings. Think of a human expert explicitly rating the clarity of an output on a scale of 1 to 5, or a domain specialist verifying the factual correctness of a detailed answer, or even automated checks for toxicity. These provide very precise numeric signals.
Sounds good, but maybe hard to get a lot of that data.
That's the downside. While precise, creating explicit rewards, especially those requiring expert human judgment, can be very time-consuming and costly to scale up.
Okay, so what's the alternative?
The alternative is implicit reward modeling. Here, rewards are inferred indirectly from observed user behaviors or interactions with the model in the wild. This could be things like whether a user clicked like or dislike on a response, upvotes on a forum, acceptance rates for suggested code, click-through rates on summaries, even how long a user engaged with a response.
Using user behavior as a proxy for preference.
Correct. This approach can accumulate vast data sets with minimal direct human annotation overhead, making it very scalable. You can get millions of data points relatively cheaply. However, it carries a significant risk of what's called reward hacking.
Reward hacking, like gaming the system.
Exactly.
Sure.
The model might learn to optimize for the proxy metric, like maximizing clicks or engagement time, at the expense of genuine content quality, factual veracity, or true helpfulness. For instance, it might learn that generating sensational or clickbaity headlines gets more clicks, even if the summary itself isn't very good. It optimizes for the easily measured signal, not necessarily the underlying quality we actually care about. So you have to be very careful with implicit rewards.
Right. Optimizing for clicks isn't the same as optimizing for truth or usefulness.
Definitely not. Furthermore, when we think about designing the reward function, especially for tasks involving reasoning, we often differentiate between outcome reward modeling, ORM, and process reward modeling, PRM.
Outcome versus process. What's the difference there?
ORM measures only the final end result. For example, in a math problem, did the model get the final answer correct? Yes or no? It's straightforward to implement and very common, especially for tasks with short responses or clear-cut answers.
Simple enough.
But for longer, multi-step responses like generating a complex piece of code, writing an essay, or deriving a mathematical proof, ORM runs into what's called the credit assignment problem. If the final answer is wrong, ORMN doesn't tell you which step in the reasoning process went wrong. It provides very limited insight into how the model reached its conclusion. It's hard to give targeted feedback.
Okay. So it fails the test, but you don't know why.
Exactly. In contrast, process reward modeling, PRM, tries to address this. It assigns feedback at intermediate steps throughout the reasoning process. It incentivizes coherent, logically consistent, and well-structured chains of thought. It looks at the path the model took to get the answer, not just the final destination.
So it rewards good thinking steps along the way.
Precisely. This is incredibly valuable for tasks like mathematical derivations, complex planning, legal arguments, or code debugging, where the process of reasoning is just as significant, if not more so, than the final output. It encourages transparency and helps ensure the model follows a robust, logical path.
That sounds much better, but maybe harder to create those rewards.
It typically requires a more complex annotation process, yes. Humans might need to mark specific gold reasoning steps or provide partial credit scoring along the way. But it can be combined with outcome rewards. Did it get the final answer right too?
Yeah.
A really strong multi-phase training signal. And what's fascinating here is that research shows PRM, especially when it evaluates the quality of the final step while considering the entire process leading up to it, can often outperform pure ORM by providing more granular, actionable feedback for the RL policy updates.
Okay, that makes a lot of sense. But models learn and change. Does the reward model ever get outdated? Or start rewarding the wrong things accidentally?
That's another excellent point and a real challenge. You can run into issues like reward hacking, as we mentioned, where the LLM finds ways to trick the reward model, or reward model drift, where the reward model itself becomes misaligned over time, perhaps by over-optimizing for a certain superficial metric that was initially a good proxy but isn't anymore as the main LLM gets smarter. To address this, researchers use iterative RL with adaptive reward models.
Iterative and adaptive, how does that work?
It's a training methodology where the LLM's performance is continuously improved by iteratively refining both the reward model and the policy model, the LLM itself, in cycles. After each round of RL training for the LLM, you collect new responses, potentially get new human feedback on those responses, and then retrain or update the reward model based on the latest model behavior and feedback. This ensures the reward signals remain accurate and relevant as the main model improves. It pushes both models, the LLM and its judge, the reward model, closer to optimal alignment with true human preferences over time, making the whole system more robust for you, the user.
So it's a continuous improvement loop for both the student and the teacher.
In essence, yes. But it raises a really important ongoing question. How do we truly ensure these reward models, whether human-trained or adapted, genuinely capture nuanced, complex, maybe even conflicting human preferences, rather than inadvertently leading to models that just get very good at optimizing for simplistic or superficial metrics? That's a deep challenge.
Okay, so once we have these sophisticated reward models, whether they're explicit, implicit, outcome-based, process-based, or adaptive, how do we actually use them to guide the LLM, to steer it towards making better decisions? This is where policy optimization comes in, right? Translating those reward signals into actual changes in the LLM's behavior. It's like refining the LLM's internal compass or decision-making engine.
That's precisely it. Instead of just learning what's statistically probable, like in pre-training, these policy optimization methods teach the LLM what's preferable according to the reward model by nudging its policy, its strategy for generating text in specific directions. The core goal of policy optimization is always to maximize the expected reward generated by our trained reward model. We're trying to find the optimal policy, let's call it PI-PHI, for the LLM, parameterized by, that generates responses, Y, for a given query, which achieve the highest possible scalar score from the reward model.
Finding the best strategy to get the highest reward.
Exactly. Modern algorithms that do this, like PPO, GRPO, and TRPO, typically rely on what are called policy gradients. A really key concept here is the advantage function, often denoted A. Imagine a video game character learning. If they perform an action like jumping in a certain situation to get a huge bonus compared to what they usually get in that situation, that action had a high advantage. If they jump and fall into a pit, that was a negative advantage.
Yeah. Okay, so it measures how much better or worse a specific action was than average.
Precisely. The advantage function quantifies how much better a specific action, like choosing a particular word or reasoning step, is compared to the expected outcome in that state, guiding the policy updates much more efficiently than just using the raw reward signal. It tells the model which specific choices were particularly good or bad. And this advantage calculation is where RL really allows models to become truly adaptable. While likelihood-based training just captures static patterns from vast corpora, RL, guided by advantage, allows models to dynamically adjust their strategies, balancing exploration, trying new things, and exploitation, sticking with what works, to improve reasoning, coherence, and alignment specifically for you, the user.
Okay, let's get into some of the specific ways they do this policy optimization. You mentioned a few acronyms, PPO, DPO, what are they?
All right, let's delve into some specific methods. First, we have odds ratio preference optimization, ORPO. This is a relatively simpler method that tries to optimize the LLM's policy directly from those pairwise human preferences we talked about earlier. Response A is better than response B. Instead of needing to train a separate reward model first and then use RL, ORPO directly updates the policy to increase the likelihood of the preferred response relative to the dispreferred one, based on their odds ratio.
So it skips the reward model step.
It aims to, yes. It integrates the preference learning directly into the policy update step. It's conceptually simpler in some ways because it avoids the two-stage process. However, it might be less flexible if you want to combine multiple complex reward signals, maybe one for helpfulness, one for harmlessness, one for conciseness, compared to methods that use an explicit, potentially multifaceted reward model.
Okay, simpler but maybe less flexible. What about PPO? You said that was common.
Yes, proximal policy optimization, PPO, is probably the most widely used and battle-tested method for policy optimization in the context of aligning LLMs with human feedback, RLHF. PPO optimizes what's called a clipped objective. It's a clever mathematical trick to keep the policy update stable. It prevents the LM from changing its strategy too drastically in a single update step, which could lead to instability or forgetting previous learning.
Keeping the changes small and controlled.
Exactly. It balances exploration, trying out variations to find better responses with stability. A key part of PPO is often the inclusion of a KL divergence penalty. Think of KL divergence as a measure of how much the LLM's new policy has drifted from its previous policy, or sometimes from the original SFT policy. The penalty acts like a guardrail or a safety brake.
A guardrail, why is that needed?
It's crucial to prevent the model from getting too obsessed with just maximizing the reward signal from the reward model. Sometimes a model can find superficial ways to get a high reward score. This is reward hacking again. But the output might become repetitive, nonsensical, or just weird. Researchers call these degenerate outputs. The KL penalty pulls the model back towards its original, more general behavior, ensuring it stays linguistically sensible and its updates remain within a safe trust region. This is critical when dealing with the incredibly complex, high-dimensional action spaces of LLMs, where things can go wrong easily.
Got it. Keep it improving, but don't let it go completely off the rails chasing the reward. What about TRPO? You mentioned that too.
Right. Trust Region Policy Optimization, TRPO, actually preceded PPO and shares a similar goal, improving stability in RL updates. TRPO enforces a hard constraint on the policy updates, explicitly ensuring they stay within a defined trust region measured by KL divergence. PPO uses a penalty or clipping, which is a softer constraint. While TRPO is theoretically very robust, calculating and enforcing that hard constraint is computationally expensive, especially for very large models. That's why PPO, which is simpler to implement and generally offers comparable performance, is usually preferred for large-scale LLM alignment tasks.
Okay, PPO is the workhorse. Then what's this newer one, DPO?
Direct Preference Optimization, DPO. This has gained a lot of traction recently. What's unique and appealing about DPO is that it directly integrates the human preference signals, A is better than B, into the model's training objective. It completely bypasses the traditional RL loop that requires training a separate reward model and then running complex policy gradient updates like PPO.
Whoa, so it skips the reward model and the complex RL part. How?
It uses a clever mathematical formulation based on the relationship between reward functions and optimal policies. Essentially, DPO directly updates the LLM to push up the probability of generating the preferred response and push down the probability of generating the less preferred response, all within a single, unified log likelihood framework, similar to standard supervised training. This simplification, no explicit reward model, no advantage calculation, no clipping or KL penalties needed during the main optimization, significantly reduces the computational overhead and implementation complexity compared to PPO.
That sounds much easier. Is there a catch?
There's often a trade-off. While simpler, DPO loses some of the granularity that you get with methods using an advantage function, like PPO. The advantage function can tell you which specific parts of a response contributed positively or negatively to the overall reward. DPO, by its nature, tends to treat entire generated sequences or trajectories more uniformly based on the overall preference label. Also, to ensure DPO works well, the preference data it's trained on needs to be relevant and high quality. Techniques like perplexity filtering are often used to pre-filter the data, retaining only responses that are on distribution or are likely for the model to generate, making the learning signal cleaner.
Interesting. Simpler, potentially faster, but maybe loses some fine-grained control. What else is out there? Oreo. Sounds tasty.
Yes. Offline Reasoning Optimization, or EO. This is an offline reinforcement learning approach specifically designed for tasks involving multi-step reasoning, like solving math problems or planning. Unlike DPO, which works directly from preferences, Oreo typically uses sparse rewards based on the final outcome, for example, was the final mathematical proof correct. Critically, it jointly trains the policy model at LLM and a value function. This value function estimates the expected future reward from any given state, enabling more fine-grained credit assignment even with sparse rewards. It helps the model figure out which intermediate steps were likely useful, even if the only feedback comes at the very end.
So it brings back that value estimation that DPO skipped.
Exactly. Oreo's explicit value function also enables useful techniques like using beam search during inference, guided by the value estimates, and iterative training where even failed reasoning attempts or trajectories can provide valuable data to refine the policy. It learns from its mistakes. The challenge with Oreo, though, is its computational cost, which can scale significantly with the length of the reasoning trajectory and the complexity of training that value model alongside the policy. Its effectiveness for math and agent tasks is shown, but generalizing it robustly to broader domains like complex coding challenges is still an area of research.
Okay, another complex one. What about GOPO?
Group Relative Policy Optimization, GRPO, is an interesting simplification of the PPO framework. Its main trick is that it eliminates the need to train a separate value function critic, which is often a memory bottleneck in PPO. Instead of learning a value function, GRPO estimates the baseline reward needed for the advantage calculation simply from the average reward of multiple outputs sampled from the current policy for the same input question.
So it compares samples against each other instead of a learned value.
Essentially, yes. It uses the group of samples to get a relative sense of performance. This significantly reduces memory usage compared to PPO with a value function and can also help stabilize policy learning. GRPO can be applied in two modes: outcome supervision, where reward is given only at the end of the output, or process supervision, where reward can be given at the end of each reasoning step, like in PRM. Using fine-grained per-step rewards in process supervision allows the model to effectively identify and reinforce high-quality reasoning steps, boosting performance in complex multi-step tasks.
Okay, a more memory-efficient PPO variant. And lastly, multi-sample comparison.
Right, multi-sample comparison optimization. This moves beyond just comparing pairs of responses, A versus B. It compares multiple responses simultaneously. By evaluating each response in the context of several others generated for the same prompt, it aims to promote more diversity in the model's outputs and mitigate potential biases that might arise from isolated pairwise comparisons. It captures more nuanced preferences and can reduce the risk of the model latching onto a single, narrow, predictable way of answering, even if it's technically preferred in pairwise comparisons. It encourages a broader range of good solutions.
Wow, it sounds like they're using incredibly sophisticated techniques, a whole toolbox of algorithms, to get these models to not just say the right thing, but to do the right thing by giving them these complex feedback loops and carefully guiding their learning.
That's exactly right. This policy optimization stage is where LLMs truly become adaptable. While likelihood-based pre-training captures broad patterns from vast text corpora, RL, through these varied optimization techniques allows models to dynamically adjust their strategies. They learn to balance exploration and exploitation to improve reasoning, coherence, safety, and alignment, specifically for you, the user, based on the preferences we teach them. Now, we've been talking a lot about human feedback driving this RL process, but is there a move towards letting AIs teach other AIs? It sounds a bit sci-fi.
It does sound futuristic, but it's happening now, and it's quite practical. Reinforcement learning from human feedback, RLHF, is, as we've discussed, the established method. It involves that three-step process: supervised fine-tuning, SFT, training a reward model based on human annotated preferences, and then using an RL algorithm like PPO for policy updates.
The standard recipe.
The standard recipe. But then we have reinforcement learning from AI feedback, RLAIF.
RLAIF. Okay, so instead of a human giving a thumbs up or down, another AI is doing the grading. That's quite a shift. How does that work? It is a shift, and it's primarily motivated by scalability. In RLAIF, you use a secondary, usually highly capable teacher, LLM, to generate those preference labels, or example, response A is better than response B, that are needed to train the reward model. This effectively eliminates, or at least greatly reduces, the need for expensive and time-consuming human annotation for the reward model training step.
So the teacher AI reads the student AI's answers and says which one it likes better.
Essentially, yes. You might prompt the teacher AI with something like, given this prompt and these two responses, which response is more helpful and harmless? And you use its generated preference labels as training data for the reward model, just like you would use human labels. The benefit is clear. It dramatically reduces the cost and time required for data collection, enabling large-scale model alignment much more efficiently.
But is the AI feedback as good as human feedback? Does the student model end up as well aligned?
That's the key question, of course. Empirical studies so far indicate that RLAIF is a very promising direction. Models trained with AI feedback can achieve performance comparable to, and sometimes even exceeding, those trained with human feedback on various benchmarks, while being much faster and cheaper to train. It offers a potentially scalable and efficient alternative to RLHF, which is a critical development for deploying aligned LLMs more broadly and making these advanced capabilities more widely available to you, the user, more quickly. Of course, ensuring the teacher AI itself is well aligned and doesn't introduce its own biases is crucial.
Right, you don't want the biases just getting passed down. Okay, to give you, our listeners, a concrete example of how these RL techniques are put into practice in a large-scale project, let's look briefly at the DeepSeek R1 approach. This was a notable project in this area. They introduced two main models, DeepSeek R10, which was interesting because it aimed for a purely reinforcement learning approach, skipping the initial supervised fine-tuning.
A bold move, relying entirely on RL from the start.
And DeepSeek R1, which used a more conventional multi-stage training pipeline, incorporating several of the ideas we've discussed. It's a very comprehensive strategy.
Indeed. Their process for the main DeepSeek R1 model provides a good illustration. The journey typically begins with a cold start RL phase. This usually involves gathering a relatively small amount of carefully curated, high-quality data to perform some initial fine-tuning on the base pre-trained model. After this preliminary fine-tuning, the main RL training is conducted, often using algorithms like GRPO, which we discussed, until the model's performance stabilizes.
Why the cold start? Why not jump straight into full RL?
That cold start phase, that initial supervised nudge, is actually critical for stability. Trying to apply purely RL-driven updates to a completely raw, pre-trained model can sometimes introduce instability and unpredictable behavior, especially early on. The initial curated data often focuses specifically on human-readable chain-of-thought reasoning patterns. As the experts behind DeepSeek noted, providing these COS-T reasoning traces before the main RL training establishes a stronger foundation for subsequent reasoning tasks. It enhances both the robustness and the interpretability of the model's thinking process later on.
Okay, stabilize it first, teach it good habits, then what?
Following that stabilization, rejection sampling and fine-tuning often come into play, particularly for improving performance on high-stakes reasoning tasks. Once the RL training has converged somewhat, a rejection sampling mechanism is used. The model generates a large number of potential responses or reasoning chains for various prompts. These are then meticulously filtered, often using automated checks or simpler models for correctness, clarity, coherence, and other quality metrics. Essentially, you pick only the best outputs generated by the RL-tuned model.
Like a very strict quality control process.
Exactly. These high-quality filtered responses are then blended with other relevant datasets to create a new, much larger corpus. And this larger, higher-quality corpus is then used for another round of supervised fine-tuning, SFT. This concept, using rejection sampling to generate better data for SFT, was also famously used in models like OpenAI's WebGPT. This process ensures that only high-quality outputs are used for further training, significantly enhancing the model's overall performance and reliability, while also expanding its coverage of general tasks and preserving the reasoning proficiency gained during RL.
So RL helps generate better data, which then improves SFT, which might then feed back into RL. It's iterative.
It can be very iterative. Then often there's a more focused, reasoning-oriented RL stage. This stage might again leverage an algorithm like GRPO, which samples a group of outputs and computes rewards. But the rewards here might be computed via more sophisticated rule-based checks, specifically targeting reasoning quality. For instance, checks to ensure correct intermediate steps in math problems, checks for properly structured chain-of-thought tags, maybe even penalties for undesired language mixing within responses if it's a multilingual model. This group-based sampling, combined with detailed reasoning-focused reward computation, ensures that the model really prioritizes high-quality, structured, logically sound outputs, profoundly enhancing its reasoning capabilities by giving it very precise feedback on how its reasoning is unfolding.
Really drilling down on the logic.
Precisely. And after achieving strong reasoning capabilities, there's often a second RL stage for human alignment. Having focused heavily on reasoning, this stage aims to further align the model with broader human preferences, focusing more on attributes like overall helpfulness, harmlessness, conversational style, maybe even creativity. This is often done by introducing additional reward signals, perhaps trained on different preference datasets, and using different prompt distributions that cover a wider range of user interactions. This second RL stage ensures the model doesn't just become a cold, logical reasoner, but also aligns with a wider spectrum of human values and expectations, making it more versatile and contextually appropriate for you, making it a better conversational partner or assistant overall.
It's like first teaching it to think straight, then teaching it good manners and social skills.
A reasonable analogy, yes.
And finally, what about making these super refined advanced models more accessible? You mentioned earlier that the initial models can be massive after all this complex training.
Right. Accessibility is key. That's where distillation for smaller models comes in. Distillation techniques are used to transfer the refined capabilities, the knowledge, the reasoning skills, the alignment learned by that large, high-performing model, like DeepSeek R1, to smaller, more efficient architectures. These might be models from families like Quinn or Llama, perhaps ranging from, say, 1.5 billion parameters up to 70 billion, which is still much smaller than the state-of-the-art giants.
So taking the wisdom from the giant brain and packing it into a smaller one.
Exactly. Think of it like taking the accumulated knowledge and skill from a chess grandmaster and effectively teaching it to a talented novice player through intensive coaching, allowing the novice to achieve competitive performance much faster than learning from scratch. This knowledge transfer allows these smaller models to inherit the advanced reasoning capabilities and alignment of the larger model, making them surprisingly competitive on challenging benchmarks, without incurring the immense computational cost of undergoing the full-scale RL training themselves.
That's fantastic. So it really helps democratize these advanced capabilities.
It absolutely does. It enables smaller, more efficient models to achieve competitive performance with significantly reduced computational overhead. This makes them much more accessible for you to deploy on more standard hardware, perhaps even on edge devices like phones or laptops in the future, bringing powerful AI closer to everyone.
Wow. This DeepSeek R1 example really sounds like a masterclass in refining an LLM from those careful baby steps at the start through multiple stages of RL and SFT, right down to distilling it for broader use. It's clearly not just about building a big brain, but meticulously sculpting and educating it. Okay, we've talked about fine-tuning to tailor models for specific tasks, making them specialists. And we've covered reinforcement learning, which aligns them with human preferences and values, teaching them how to behave. Now, let's explore the third major pillar, test time scaling, or TTS. This area is fascinating because it's all about boosting an LLM's performance right when it matters most during inference. That's when the model is actually generating an output for you.
Exactly. And the key distinction here is that TTS techniques typically enhance performance without altering the core model architecture or weights. The trained model itself stays the same.
So you're not retraining it.
Generally not. It's about optimizing how the model thinks or processes information on the fly at the moment you ask it a question, making it smarter in that specific instance.
Okay, making it think harder when needed. How do they do that?
One of the fundamental ways we see this in action is through more sophisticated decoding strategies, moving beyond just greedily picking the single most likely next word at each step. We see things like beam search and best-of-n search.
Beam search. That sounds familiar, maybe from older AI.
It's been around for a while, yes, used in machine translation and speech recognition for decades. For LLMs, instead of just picking the single highest probability next word, beam search keeps track of the top n most probable partial sequences. This set of sequences is called the beam at each step of generating the output.
So it keeps a few options open at each step.
Exactly. It systematically explores multiple probable paths or continuations in parallel. Imagine you're writing a complex sentence, and you mentally consider a few different ways to phrase the ending, exploring each branch slightly before committing. Beam search does something similar computationally. This improves the chances of finding a globally better, more correct, and coherent final sequence, especially in tasks like translation, where many word choices could lead to a valid output, summarization, or even in structured reasoning frameworks like tree of thoughts, which we'll get to. It explores more possibilities than just the single most obvious path.
Okay, exploring multiple paths. What about best of n?
Best-of-n search, which is also sometimes called rejection sampling in this context, takes a slightly different approach. With best-of-n, the model simply generates n-complete, independent candidate outputs for the given prompt, usually using diverse sampling methods to get variety. Then, after generating all n candidates, it picks the single best one based on some chosen criterion. Often this criterion is the score from a reward model, similar to the ones used in RLHF.
So generate a bunch of answers, then pick the winner.
Pretty much. This allows for potentially greater diversity in the generated responses compared to beam search, because each candidate is generated almost independently from start to finish. Beam search incrementally builds and prunes hypotheses along the way. The trade-off is usually higher computational cost for best of n because you're generating multiple full responses.
Does best of n work well?
It can work surprisingly well. With a robust reward model guiding the selection, best of n can sometimes approach or even match the performance achieved through full RLHF training. So instead of the model just giving us the first answer that pops into its head, these methods are essentially making it try out a bunch of different answers or different ways of thinking before picking the best one to show you. Generally, beam search might be more effective for harder questions or when you have a tighter compute budget, while best of n can scale better for easier tasks where getting one good answer out of many samples is likely. It highlights that constant trade-off between exploration depth and computational expense.
Makes sense. Try harder or try more options. Are there ways to be even smarter about when to use more computation?
Yes, that's exactly the idea behind compute optimal scaling, COS. This is a dynamic strategy that tries to cleverly allocate computational resources during inference based on the perceived difficulty of the input prompt you provide.
So it figures out if my question is easy or hard. How?
It can be done in a couple of ways. Sometimes prompts are categorized beforehand based on known success rates. Other times, the model itself might be trained to predict the difficulty of a prompt or use its initial confidence levels as a proxy for difficulty.
Okay, and once it knows if it's easy or hard, what does COS do?
The adaptive strategy is quite elegant. For prompts deemed easier, the model might undergo just sequential refinement. It generates an initial answer and then iteratively improves it with minimal additional computation, maybe making small edits or adjustments until it reaches a satisfactory state. But for prompts categorized as harder, COS intelligently triggers more computationally intensive methods like parallel sampling, similar to best of n or beam search. It dedicates more resources to exploring multiple variations and reasoning paths to increase the likelihood of finding a correct or high-quality solution.
Tailoring the effort to the problem.
Precisely. This dual approach cleverly balances thorough exploration for challenging inputs with efficient refinement for responses that are already likely close to correct. The efficiency gain can be remarkable. Studies have shown COS achieving performance equivalent to traditional best-of-n sampling, but using up to 4 times lower compute usage on average. It's like having a smart thermostat for your LLM's inference compute, dynamically adjusting the effort based on input complexity. This leads to more efficient and cost-effective deployment for you, allowing you to get high-quality answers without necessarily paying for peak compute effort every single time.
That's incredibly clever. So beyond just generating multiple outputs and picking the best, how do these models actually structure their thinking process at test time to perform really complex reasoning, almost like a human brainstorming or outlining a potential solution?
This brings us to a fascinating set of techniques, often grouped under structured thought methods. These have evolved significantly from just basic prompting. Chain of thought, co-prompting, which we mentioned in fine-tuning, is also a foundational technique here at inference time. Simply adding a phrase like, "let's think step by step," to your prompt can induce an LLM, if it's capable, to produce intermediate reasoning steps before giving the final answer. Just that simple phrase can trigger it. In sufficiently large and capable models, yes. It seems to unlock a latent ability trained during pre-training or fine-tuning. This significantly improves performance on multi-step inference tasks, math word problems, logical puzzles, multi-hop QA where the answer depends on connecting several pieces of information. Relatedly, fine-tuning models specifically to revise answers sequentially allows them to build on previous attempts, improving accuracy over time, especially for easier questions. While for harder questions, exploring multiple parallel paths, like in sampling, often proves more beneficial.
Okay, so co helps structure the thinking. What builds on that?
Building directly on QT is self-consistency decoding. This is a clever decoding strategy. Instead of just generating one chain of thought, you prompt the model to generate multiple, diverse reasoning chains for the same problem, perhaps using sampling with some randomness temperature. Then, instead of trusting any single chain, you look at the final answers produced by all these different reasoning paths and select the answer that is the most consistent across them, essentially. You take a majority vote.
Like asking several experts the same question and going with the consensus answer.
Exactly that principle. It leverages the idea that while the model might make a mistake in one reasoning path, it's less likely to make the same mistake across multiple diverse paths. This significantly improves correctness on arithmetic and logical reasoning problems, often without requiring any new training, just extra sampling compute during inference. It's a powerful ensemble approach that allows the model to effectively cross-verify its answers internally.
Very neat. Okay, what about tree of thoughts? That sounds more complex.
It is. Tree of thoughts, TOTI, aims to generalize chain of thought. Instead of just a single linear chain, 2T allows the model to explicitly explore multiple possible thought sequences or reasoning paths, formulating the reasoning process as searching through a tree structure. It's inspired by how humans often solve complex problems. We consider different possibilities, explore branches, maybe backtrack if one path isn't working. TOTI allows the model to generate several candidate next thoughts or intermediate steps, evaluate their potential, and then strategically navigate this tree using search algorithms like beam search or breadth-first search.
So it can branch out and backtrack.
Exactly. It allows for look-ahead, evaluating potential future steps, and backtracking, abandoning unpromising paths. This makes it especially useful for complex problems that might require exploring different strategies, like puzzles, for e.g. Game of 24, planning tasks, or even certain types of creative generation. It consistently outperforms simpler COTI methods on these kinds of challenging tasks. And what's compelling here, as some research suggests, is that investing inference time computation like this, making the model think harder, via search can sometimes yield better results than simply scaling up the model's parameters during pre-training, especially for really difficult reasoning tasks like advanced math problems.
Spending compute at inference time can be better than spending it at training time sometimes.
Interesting.
And graph of thoughts, even more complex.
Even more flexible, potentially. Graph of thoughts, GAT, extends the tree of thoughts idea. Instead of being restricted to a strict tree structure where each thought has only one parent, GAT enables more flexible and potentially efficient reasoning by representing thoughts and their dependencies as nodes and edges in a general graph structure.
How is a graph different from a tree in this context?
In GAT, thoughts are nodes that can have adaptable dependencies. A thought might draw upon multiple previous thoughts, not just one parent. This framework explicitly supports key transformations that are harder in a strict tree. Aggregation, merging multiple parallel lines of reasoning or partial solutions. Refinement, iteratively improving individual thoughts based on later insights. And generation, producing diverse candidate thoughts at any point. Crucially, GAT can overcome TET-TD's sometimes restricted backtracking capabilities by allowing iterative refinement of any previous thought in the graph, not just moving up and down branches. This enhanced flexibility aims for greater problem-solving efficiency and adaptability, making it potentially superior for tasks requiring truly complex nonlinear reasoning, where ideas might connect and loop back in intricate ways.
Wow. It's incredible to think of these models not just generating words sequentially, but actually mapping out their thought processes like we might, with different paths, dead ends, loops, merging ideas, even self-correction. It's almost like they're becoming introspective.
Introspective is an interesting word for it. And indeed, these models are also getting much better at self-correction and confidence estimation during inference. One approach is confidence-based sampling. Here, an LLM might generate multiple candidate solutions or reasoning paths, and then it prioritizes or selects among them based on its own internal confidence in each outcome.
How does it know its own confidence?
It can be estimated in various ways. Sometimes it's simply the log probability assigned to the entire generated sequence. Higher probability might mean higher confidence. Other times, the token probabilities generated at each step can be used to guide exploration in a reasoning tree like 2T, biasing the search towards paths the model seems more certain about. It's like a student who reviews their multiple choice answers and has a gut feeling about which one is most likely right based on how easily it came to mind.
Okay, trusting its own judgment. What about getting a second opinion?
That's the idea behind search against verifiers. This is another powerful technique to enhance answer quality. Again, you generate multiple candidate responses, but this time you select the best one using automated verification systems. Typically, a proposer, LLM, generates the candidates, and a separate verifier, which could be another specialized LLM, a simpler model, or even a set of heuristic rules, judges these candidates based on predefined criteria.
And what do these verifiers check?
Verifiers come in two main flavors, similar to our reward models. You can have outcome reward models, ORM, as verifiers which judge only the final answer's correctness. For example, is this math answer right? Or you can have process reward models, PRM, as verifiers which evaluate the logical coherence and soundness of the intermediate reasoning steps themselves. ORM verifiers are suitable for tasks where final correctness is easily checked in binary. PRM verifiers are especially useful in multi-step reasoning, as they can provide more granular feedback to prune invalid or illogical reasoning paths early on during the search process, making the overall search more efficient and reliable.
Got it. Verify the outcome or verify the process.
Yeah.
And can they improve themselves without an external verifier?
Yes, that falls under self-improvement via refinements. This refers to a family of techniques where LLMs iteratively enhance their own outputs through self-evaluation and revision, acting as their own critic. Self-refinement, for example, involves an LLM generating an initial response, then prompting itself, or being prompted, to critically examine that response. Is this answer correct? Is it clear? Are there flaws in the reasoning? And then generating a refined output based on that self-generated feedback. This iterative process can continue for several rounds.
Like an author writing a draft, then editing and revising it based on their own critique.
Exactly that loop. Self-polish is a related approach where the model might even try to progressively refine the problem statement itself to make it more comprehensible or solvable, perhaps by rephrasing or restructuring the input query to improve its own understanding before even attempting a solution. These self-improvement methodologies really emphasize active reasoning and leveraging internal feedback mechanisms over just passively generating an answer based on static pre-training. They lead to potentially greater consistency and accuracy over time.
Okay, self-critique, that's sophisticated. What about Monte Carlo tree search? That sounds like it comes from game-playing AI.
It does. Monte Carlo tree search, MCTS, was famously a core component of Google DeepMind's AlphaGo, which mastered the game of Go. MCTS is a powerful search technique that builds a decision tree by performing many random simulations or rollouts. Starting from a current state, like a partial reasoning chain, it explores different possible continuations by randomly sampling actions, simulates the outcome, for example, does this path lead to a correct answer, and uses the results of many such simulations to estimate the value of different choices, intelligently guiding the search towards more promising branches.
So it plays out many possibilities randomly to see what works best.
In essence, yes. For LLMs, this means the model can look ahead by simulating many possible continuations of its thought process and make more informed reasoning choices based on the empirical success rates observed in these simulations. It's like a chess player, considering many possible future move sequences. MCTS has been applied to LLMs for tasks like query planning, figuring out the steps needed to answer a complex question, and code generation, helping the LLM pick the chain of thoughts or generate the code snippet with the highest likelihood of success based on these simulated rollouts.
Wow, and Satori, chain of action thought.
Chain of action thought, Satori, is a more recent and quite integrated paradigm. It combines several ideas in a two-stage training process. First, there's format tuning. This uses synthetically generated data to explicitly teach the model specific reasoning formats, often incorporating special meta-action tokens that represent steps like retrieve information or verify calculation. It teaches the model how to structure its thought process for specific tasks. Second, there's self-improvement via RL. This uses an RL algorithm like PPO to further refine the model's reasoning abilities. A key aspect here is often a restart and explore strategy. If the model realizes, perhaps via its own critique or a verifier, that it's gone down a wrong reasoning path, it can restart from an earlier intermediate step and explore alternative paths. Rewards in this RL phase are typically based on final correctness, bonuses for good self-reflection or critique, and possibly feedback from an outcome reward model.
So it learns a format, then learns to improve within that format using RL and backtracking.
Exactly. This approach allows the model to potentially allocate more computational resources to tougher problems by exploring more alternatives, and extend its reasoning process during testing for complex tasks, making it both flexible and robust.
This really changes the game, doesn't it? It's moving beyond just answering. It's about teaching the model to question its own answers, to verify its reasoning, to backtrack, to actively improve itself right when you need the answer. It's a huge step towards more reliable AI.
It absolutely is. And it highlights a really critical strategic trade-off that developers and researchers constantly face in LLM development, the balance between pre-training versus test time scaling.
Right, invest compute up front in training, or invest it on the fly during inference.
Precisely. Pre-training, as we know, involves scaling model parameters, making bigger models, or increasing the amount and diversity of training data. This requires substantial upfront computational investment. These larger models, with deeper knowledge and reasoning capabilities baked into their parameters, are generally superior for the absolute hardest foundational tasks, or in situations where inference compute constraints are very high, meaning you need answers almost instantly with minimal extra processing.
Bigger brain, faster recall.
In a sense. Test time scaling, TTS, on the other hand, focuses on optimizing the compute used during inference. It leverages techniques like iterative refinements, search-based decoding, beam search MCTS T2T, adaptive sampling COS, and self-correction, all typically without modifying the base model's weights. This approach can be incredibly efficient from a training cost perspective and surprisingly effective at inference. For example, studies have shown that TTS techniques can allow a smaller model to achieve results comparable to a model 14 times larger on easy to intermediate difficulty tasks, while potentially reducing the inference compute cost, measured in FLOPs, by a factor of 4 in compute-intensive scenarios compared to naive sampling.
So spending compute smartly at inference can make a smaller model punch way above its weight.
It can, especially for tasks where the base model already has reasonable competence, but needs help structuring its reasoning or avoiding simple mistakes. Test time compute is definitely not a one-to-one replacement for pre-training. You can't just use TTS to make a tiny model understand quantum physics if it wasn't trained on it. But it offers a very viable alternative or complement in many cases, especially for you if your inference budget is flexible and you can tolerate a slightly longer generation time for more complex queries in exchange for higher accuracy or reliability from a smaller, cheaper-to-run base model.
So when do you choose which approach?
It's a strategic decision. TTS is incredibly useful for scenarios with flexible inference budgets, or when you want to extract maximum performance from existing base models that already have reasonable competence in a given domain. Conversely, pre-training, or extensive fine-tuning, remains essential for tasks requiring fundamentally new knowledge or capabilities, like reasoning about completely novel domains, where inference time optimizations alone might not suffice because the underlying knowledge simply isn't there in the base model. But importantly, these two approaches are often highly complementary, not mutually exclusive. The future of LLM systems may very well involve a hybrid approach, perhaps using moderately sized base models pre-trained with essential world knowledge and core reasoning skills, combined with sophisticated TTS techniques that dynamically enhance responses with on-demand computation for specific, complex, or high-stakes queries. This synergy could enable more cost-effective, efficient, and adaptable large-scale model deployment.
That makes sense. Use the right tool for the job, or combine them.
It really raises an important question for anyone deploying or using these models. For your specific needs and constraints, should you prioritize foundational capabilities through massive pre-training, or focus on achieving accurate, context-aware refinement via test time scaling with a smaller model? Often, the most powerful and practical solutions will involve finding the right strategic combination of both.
Okay, so after all this incredible work, pre-training, fine-tuning, reinforcement learning, test time scaling, it's not just about building them, it's about making sure they actually work for us, right? That they're helpful, accurate, safe. This is where rigorous testing comes in. How do we actually know if all these sophisticated post-training techniques are genuinely making LLMs better? How do we measure success?
That's a critical question. You need robust ways to measure progress and effectiveness. A diverse set of benchmarks is absolutely crucial to evaluate LLM post-training performance comprehensively. These benchmarks need to cover multiple dimensions of capability: core reasoning abilities, alignment with human preferences, multilinguality, general language comprehension, and performance on specific tasks like dialogue or information retrieval.
So not just one test, but a whole battery of tests covering different skills.
Exactly. A multidimensional view. This comprehensive evaluation ensures we have a thorough understanding of an LLM's strengths and its limitations across various applications. Think of it like a really thorough final exam for the model, testing different facets of its intelligence, knowledge, and utility. As the saying goes, knowledge is most valuable when understood and applied correctly. These benchmarks provide the structured framework essential for assessing post-training effectiveness and ensuring the model's real-world applicability and reliability for you, the user. They are absolutely vital for guiding the fine-tuning process, calibrating model behavior, ensuring alignment, and optimizing the overall system. They directly drive improvements in response accuracy, robustness, and desired behavioral compliance.
Okay, so what kinds of benchmarks are we talking about? Can you give us some specific examples in different categories and explain how they help push the field forward?
Certainly. We can group them into several key categories based on what they're designed to measure. First, we have reasoning benchmarks. These are designed specifically to assess an LLM's ability to perform logical, mathematical, and scientific reasoning areas where simple pattern matching often falls short. Examples include datasets like math and GSM-8K, which contain challenging math word problems requiring multi-step arithmetic reasoning. MetaMath QA is another focusing on math problem solving. For scientific understanding and reasoning, sometimes involving multiple modalities like text and images, there are benchmarks like WorldTree V2 and MMMU. And PangaBench even extends reasoning evaluation into multilingual and cross-cultural contexts.
But these tests really push the models on logic and problem solving.
They do. They help determine how well models can process structured knowledge, apply deductions, and follow complex instructions, which is critical for tasks requiring deep understanding beyond simple information recall. Success here often correlates with effective code T fine-tuning or advanced test time search strategies.
Makes sense. What about alignment? How do you measure if a model is helpful, honest, and harmless?
That's where RL alignment benchmarks come in. These are absolutely central to evaluating and refining response generation based on human preferences, managing unwanted outputs, and ensuring user-aligned behavior, typically driven by RLHF or RLAIF. Examples include datasets like help steer and ultra feedback. These often involve collecting human judgments on multiple attributes of a response simultaneously, like how helpful is it? How well does it follow instructions? Is it creative? Is it harmless? This provides a nuanced score for alignment. Anthropic's HHRL-HF dataset specifically focuses on training and evaluating models for harmlessness through preference optimization, teaching them to avoid generating harmful, unethical, or biased content. Then there are benchmarks borrowed from traditional RL, like D4RL, datasets for deep data-driven reinforcement learning, meta-world simulated robotics tasks, and even MineRL, learning from interactions in Minecraft. While not text-based, these have broader implications for evaluating how LLMs make sequential decisions and learn complex behaviors in interactive settings, which is relevant even for chatbots.
Okay, measuring helpfulness and harmlessness. What about different languages?
Crucial area. Multilingual evaluation benchmarks are essential for ensuring that models don't just perform well in English, but can generalize across languages, adapt through translation, and support fine-tuning even for low-resource languages with less available data. Think of it as testing the LLM's global adaptability. Datasets like Culture X and Pangenes evaluate capabilities like cross-lingual tokenization, translation quality, and instruction following in a huge number of languages, sometimes over 150. Others like TIDA-QA focus on question answering in typologically diverse languages, and MMEvil targets task-oriented multilingual evaluation. These benchmarks drive improvements in LLM fine-tuning across diverse linguistic contexts, ensuring the benefits aren't just limited to English speakers and making the models truly useful globally.
Good. What about just general understanding and conversation?
Right, general comprehension benchmarks. These contribute broadly to model fine-tuning, evaluating response coherence, factual accuracy across diverse topics, and overall conversational quality based on user preferences. Big Bench, beyond the imitation game benchmark, is a massive collaborative benchmark designed to probe LLMs on a vast range of challenging tasks requiring deep comprehension. MMLU, Massive Multicast Language Understanding, measures correctness and informativeness across a wide spectrum of academic and professional subjects, from elementary math to law and history. And then there are benchmarks specifically focused on conversational evaluation, often involving direct human judgments. Chatbot Arena, run by LMSYS, famously pits anonymous models against each other and uses crowdsourced votes to rank them based on perceived quality. MTBench uses strong LLMs to automatically evaluate chatbot responses across multiple dimensions. Reward Bench focuses specifically on evaluating the quality of reward models themselves. These datasets are critical for refining LLM fluency, factual correctness, open-ended response generation, and ensuring they are genuinely helpful and pleasant for you to interact with.
And finally, dialogue and search. Getting information.
Yes, dialogue and search benchmarks. These are key for optimizing tasks, where the LLM needs to engage in coherent multi-turn conversations or retrieve and synthesize information accurately. Datasets like Convey-II and Multi-Value-OC evaluate multi-turn conversational models, focusing on aspects like dialogue state tracking, remembering context, and generating appropriate responses over long interactions. These are essential for fine-tuning chatbots to feel natural and intelligent. For search and information retrieval, benchmarks like BA, benchmarking IR, provide large-scale datasets with human-annotated relevance judgments, used for fine-tuning models that need to rank search results effectively. Tree-crack deep learning tracks like DL2122 focus specifically on document relevance ranking and fact retrieval accuracy, pushing LLMs to be powerful tools for finding precise and reliable information when you ask them to search. Each of these benchmark categories plays a vital role. They provide the targets, the measuring sticks, that guide researchers and developers in ensuring that all the complex post-training methods we've discussed are truly effective in improving LLM performance in ways that matter for real-world scenarios and ultimately meet your needs and expectations as a user.
Okay, so we have all these methods for refining models and benchmarks to measure how well they work. It's clear that the researchers aren't slowing down, though. They're constantly innovating. Looking at the trends in research activity, maybe referencing some of the analysis in the source material we looked at, where is the cutting edge heading? What are the hot topics and the big problems they're most focused on solving right now?
That's right, the field is moving incredibly fast. If we look at research trends, visualize perhaps in figures tracking publications or focus areas. In RL for LLMs, there's definitely a noticeable, sustained increase in research activity. A strong focus continues to be on human-in-the-loop RL, which really emphasizes the ongoing demand for interactive approaches where human feedback continually refines models, but also highlights the need for making this process more scalable and efficient.
Keeping humans involved, but maybe more efficiently.
Exactly. Concurrently, interest in reward modeling itself is steadily rising. We're seeing particular excitement around concepts like self-rewarding language models, where models try to generate their own reward signals or critiques, potentially reducing the need for external feedback. However, significant challenges remain here, like avoiding reward hacking. where models learn to exploit superficial metrics without delivering true underlying value, and the fundamental difficulty of designing reward functions that are truly robust, capture complex nuances, and are aware of potential failure modes.
Getting the reward right is still hard. What about making the models think better at inference time?
Right, for decoding and search strategies, sophisticated methods like tree of Gauss and applying Monte Carlo tree search for LLM reasoning are definitely pushing the boundaries of LLM reasoning and complex decision-making. They allow models to explore possibilities more deeply. But these powerful search techniques come at a cost. They demand reliable uncertainty estimators, ways for the model to know when it's unsure or when its particular path is unlikely to succeed to manage the potentially huge computational overhead. We need smarter ways to know when it's worth investing that extra thinking time.
And making them safer, more trustworthy.
Absolutely paramount. Robustness and safety are huge areas. Research into bias-aware RL is growing, focusing on developing methods that allow models not just to avoid generating biased content, but potentially to identify and actively reduce undesirable biases learned from their training data. This is crucial for trustworthy fine-tuning. Similarly, uncertainty-aware RL aims to make models more transparent about their own limitations. Teaching models to accurately signal when they don't know something or when they have low confidence in an answer is critical for building user trust and reliability.
That I don't know answer is so important sometimes.
It really is. In personalization and adaptation, a major focus is on privacy-preserving RLHF. How can we tailor models to individual user needs and preferences without compromising sensitive user data? This directly connects to challenges in on-device adaptation, where the goal is to enable models to learn and adapt directly on your personal devices, like phones or laptops, without sending private interaction data to the cloud.
Keeping your data private while still getting a personalized experience. Tricky.
Very tricky. And finally, regarding process versus outcome reward optimization, the trend seems to favor process reward modeling currently. Research focusing on iterative strategies that provide feedback on intermediate reasoning steps appears to dominate over simpler outcome-based metrics, especially for complex tasks. This suggests a growing recognition that understanding and guiding how a model thinks is often more effective than just judging its final product.
Okay, so it's a really dynamic landscape. Trends point towards more adaptive, interactive, robust, private, and process-aware LLMs. But what are the specific obstacles they're still grappling with? What are the big headaches keeping researchers up at night?
There are several critical obstacles, persistent challenges that the community is actively working on. One major headache in fine-tuning, especially ongoing fine-tuning, is catastrophic forgetting.
Catastrophic forgetting. Sounds bad.
It is. This is the phenomenon where LLMs, when updated or fine-tuned on new data or tasks, can suddenly lose or significantly degrade capabilities they had previously learned. It's like training a student intensely on physics, only for them to completely forget the calculus they learned last semester. Even parameter-efficient fine-tuning methods like LoRa don't entirely solve this problem. Future directions here include exploring more sophisticated continual learning strategies, developing better regularization techniques, like LoRa, mentioned in the source, that explicitly protect old knowledge, using curriculum-based fine-tuning that introduces new facts or skills gradually, and designing hybrid training approaches that might combine fine-tuning with retrieval from external knowledge bases, retrieval-augmented fine-tuning.
Trying to learn new tricks without forgetting the old ones.
Exactly, and maybe also explicitly training models to represent uncertainty better, allowing them to recognize when a query falls outside their expertise, learn during pre-training, and perhaps respond with, "I don't know," or defer to an external reliable source. That would be incredibly useful for you as a user.
Definitely. What other big challenges?
Another major area is safe fine-tuning and the inherent privacy risks. The data used for fine-tuning, especially instruction following or dialogue data, often contains sensitive or personal information. This creates privacy vulnerabilities. Techniques like membership inference attacks, figuring out if your data was used in training, or even data extraction attacks, getting the model to regurgitate specific training examples, are real concerns. Mitigating these risks effectively while maintaining model utility is an open problem. Researchers are actively exploring differential privacy fine-tuning, which involves adding carefully calibrated noise to the model updates to obscure individual data contributions. Federated fine-tuning, where the training data never leaves the user's device, is another promising direction, especially for on-device adaptation. However, these privacy-preserving techniques often come with trade-offs. They might slightly reduce the model's accuracy or require careful tuning to balance privacy and utility effectively.
The privacy-utility trade-off. Always tricky. And what about the human feedback itself?
Right, the limitations of human feedback. While RLHF has been incredibly successful, relying solely on direct human preference labels is inherently costly, time-consuming, and can be quite subjective or inconsistent. Different people might have different preferences. This is why techniques like reinforcement learning from AI feedback, RLAIF, and other forms of automation are gaining so much traction. Using AI models to generate preference labels or critiques can vastly scale the alignment process. Concepts like constitutional AI, developed by Anthropic, use a predefined set of principles or rules and another AI model as a judge to critique and refine responses, reducing the need for constant human oversight for every single decision. Emerging directions even explore having multiple AI agents debate a question or critique each other's outputs, using their consensus or disagreement as a reward signal. This could potentially scale the tuning process even further. However, this also raises new, critical questions about ensuring the AI judge or judges are themselves well-aligned and don't just create echo chambers of biases if they only learn from other AIs without grounding in human values. Blending human and AI feedback in sophisticated, perhaps hierarchical, schemes seems like a very promising path forward, trying to get the scalability of AI with the grounding of human judgment.
Combining human wisdom with AI skill makes sense. So the goal is always to push the boundaries, make them more capable, more efficient, maybe integrate them into even more complex systems. What's next on that frontier? What are the cutting-edge concepts we should be keeping an eye on?
Absolutely. Pushing boundaries is the name of the game. In test-time scaling, a key challenge is how to efficiently and reliably orchestrate these complex inference time processes, like search or self-correction, and dynamically allocate compute resources where they're most needed. Future directions here include developing more adaptive systems that can accurately estimate query complexity on the fly, creating more reliable confidence metrics for the models themselves so they know when they need to think harder, and exploring more efficient probabilistic inference techniques using Monte Carlo methods that might achieve high accuracy with fewer computationally expensive rollouts or simulations. Another interesting idea is distilling the results of these expensive test-time computations back into synthetic training data, essentially teaching the base model the patterns of smarter thinking discovered during inference, creating a synergistic loop between training and inference optimization.
Teaching the model the results of its own smarter thinking. Clever. What about reward modeling?
For reward modeling and credit assignment, persistent problems include reward misgeneralization, where a model learns a reward function that works well on the training data but fails to generalize correctly to new situations, and dealing with sparse rewards in long, multi-step tasks where feedback only comes at the very end. Future research is looking at hybrid reward models that combine the strengths of process-based and outcome-based feedback, developing step-level policy optimization algorithms for more granular control over the learning process, exploring dynamic credit assignment techniques borrowed from classical RL, like temporal difference learning, and failure-aware training methods that specifically incorporate negative examples or failed trajectories to improve robustness and prevent the model from repeating mistakes.
Making the rewards smarter and learning from failure. And efficiency. RL sounds expensive.
Efficient RL training and distillation are critical areas, you're right. Current RL methods, especially PPO with large models, are computationally very expensive, and sometimes, surprisingly, simpler knowledge distillation, just training a smaller model to mimic a larger one's outputs, can outperform complex RL alignment. So, future directions involve creating hybrid frameworks where RL policies are perhaps initialized with knowledge distilled from a stronger teacher model, using curriculum sampling strategies to make the RL training data more effective, and leveraging PEST techniques during the RL updates themselves to keep the computational costs down. For example, combining PRM-guided tree search with online distillation, where the model learns from search results as they happen, has shown potential for significant efficiency gains, maybe up to 4x, while maintaining high accuracy.
Finding ways to get the benefits of RL without the massive cost. What about privacy and personalization?
Privacy-preserving personalization remains a huge goal. How do we customize models to individual users' needs, styles, and data without exposing their private information? Active research areas include homomorphic instruction tuning, performing computations on encrypted data, achieving differential privacy via adding noise to reward signals or gradients during RLHF, and federated distillation, where a central model's knowledge is distilled to local models on user devices without raw data ever leaving the device.
Moving beyond just one giant model.
Exactly. As single model scaling might be approaching physical or economic limits, collaborative multi-model systems are gaining a lot of traction. This isn't just about one LLM, but teams of them. Research here explores multi-agent LLM collaboration, where different specialized agents might handle different parts of a complex problem. Maybe one generates ideas, another critiques them, a third verifies facts. It involves developing emergent communication protocols, allowing these agents to coordinate effectively, building robust ensembles where different models might specialize based on analyzing each other's failures, and even exploring gradient-free synergy learning, where agents learn to cooperate effectively without needing direct gradient sharing.
A whole team of AIs working together.
Potentially. And extending this to richer data, multimodal RL integration is key. How do we apply these RL alignment techniques effectively when the model is dealing with text, images, audio, maybe even video simultaneously? A major challenge here is the combinatorial state explosion. The number of possible states and actions becomes astronomically large. Future directions involve developing hierarchical attention frameworks that can focus on relevant modalities, adaptive truncation strategies to compress long multimodal contexts efficiently, and perhaps flash curriculum approaches that introduce multimodal capabilities progressively during training, making it feasible to train robust models on these incredibly rich data types.
Wow. And finally, just overall efficiency, making them think fast and smart.
Yes, overall efficiency is a constant concern, especially with complex reasoning. Researchers have noted an overthinking phenomenon, where models sometimes waste significant computation generating excessively long or convoluted reasoning chains that don't actually improve the final answer. Analysis mentioned in the source suggested potentially 22% wasted compute in chains, exceeding their optimal length. So future directions include developing partial rollout strategies in search algorithms, stopping exploration early if it doesn't seem promising, adaptive length penalty mechanisms during generation, and hybrid architectures that might combine the broad exploration of MCTS with the fine-tuning capabilities of advanced RL optimizers like PPO or GRPO, all aimed at making the models both smarter and more computationally frugal.
So much going on. But are there still some really fundamental roadblocks, things that are proving particularly tough?
Absolutely. Despite all this progress, several significant open challenges persist that the research community is actively tackling. Uncertainty propagation, for instance, reliably estimating and using model confidence, still adds a noticeable latency overhead, maybe around 18% according to some estimates, which can be problematic for real-time applications. Catastrophic forgetting, as we discussed, remains a major issue, potentially causing around 29% degradation of base model capabilities during standard RL fine-tuning if not carefully managed. Benchmark saturation is another concern. Simply chasing higher scores on existing academic benchmarks like MMLU doesn't always correlate well with improved real-world performance or user satisfaction, suggesting we need better, more holistic evaluation methods. And adversarial vulnerabilities are still a serious problem. Techniques like prompt injections, designed to trick the model into ignoring its safety instructions, still show a high success rate against many models, especially with gradient-based attacks, highlighting the ongoing challenge of making these models truly robust against malicious use.
So what does this all mean for you, our curious listener? It means the world of LLMs is still evolving at an absolutely blistering pace. Researchers are constantly striving to make these tools smarter, safer, more efficient, and more aligned with our needs, pushing the boundaries of what's possible with artificial intelligence every single day. Hashtag tag tag outro.
Well, we've certainly taken a deep dive today. We've journeyed through the really intricate world of LLM post-training. We started with fine-tuning, seeing how it tailors models for specific jobs. Then we explored reinforcement learning, the key to teaching them human preferences and desired behaviors. And finally, we looked at test time scaling, which lets them think smarter and harder right when you need an answer.
We've seen how these different methodologies, SFT, reward modeling, PPO, DPO, PFTT, TOTI, self-correction, and all the rest work together. They're all part of this crucial process of transforming that raw computational power of a pre-trained model into something much more refined, aligned, reliable, and ultimately incredibly useful AI. It's clearly a field grappling with this complex balance, isn't it? The balance between raw power on one side and nuanced control, safety, and alignment on the other. Researchers are constantly pushing the boundaries of what these models can do, but also how well, how reliably, and how responsibly they can do it.
Absolutely.
Yeah.
And the ultimate goal behind all this complex research is quite clear: to make these powerful AI tools more dependable, more accurate, more helpful, and more aligned with human values and intentions, ultimately for your benefit as a user.
So, to leave you with something to think about, as these LLMs become increasingly adept at things like sophisticated reasoning, self-correction, maybe even self-improvement, potentially without constant human intervention, What new practical considerations or maybe even ethical questions do you think will emerge regarding their autonomy and decision-making, especially if they get deployed in critical applications like medicine, finance, or education?
That's a profound question for all of us to consider as this technology continues its rapid advance. And for those of you eager to track these developments more closely yourself, the researchers whose work informed much of our discussion today have generously provided a public repository compiling resources on this topic. You can find it on GitHub at github.com/COIAutupi at DEA. Yeah, it's awesome. LLM Post Training.
Got it.
It's a fantastic resource for staying informed in this incredibly fast-evolving field.
Excellent. Well, that's all the time we have for this deep dive. Thanks for joining us.